G'day, in this video we're going to be unpacking the Schrödinger equation and looking at how it explains the nature and behaviour of electrons in orbitals. Today's lesson focuses on dot point 8.3.5, where we're being asked to analyse the contribution of Schrödinger to the current model of the atom. There's quite a lot that we need to unpack to get there though. We need to understand the concept of quantum numbers, as they're quite closely related to Schrödinger's equation. This equation brings in the concept of quantum numbers as well as de Broglie's concepts about the wave nature of matter, and we'll be looking at how Schrödinger built upon these ideas to develop his wave equation and what the qualitative consequences of that equation is. This equation is quite complex and is not something that is actually within scope of the syllabus or the course itself, but rather we need to have an appreciation for, again, those qualitative consequences and how it led to the improvement in our model of the atom and our understanding of the behavior of subatomic particles. Once we've got an understanding of this work, we'll talk about the contributions and limitations and also introduce the idea of the Pauli exclusion principle, which is always talked about hand in hand with our Schrödinger concepts. Again, this is not a direct part of our syllabus, but learning and understanding the consequences of the Pauli exclusion principle will help give us a better understanding of the mechanics of the Schrödinger equation. So let's start with this idea of quantum numbers. In some part, quantum numbers is a concept that you are already familiar with. We already have an understanding of the principal quantum number. It describes the size and the energy associated with an orbital, their integer values from 1, 2, 3, and onwards. These are associated with the orbitals that exist in the Bohr model. However, there are other quantum numbers which describe the nature and behavior of subatomic particles. And since the beginnings of the principal quantum number highlighted by Bohr, physicists after this time began working on describing other types of properties of particles using these quantum numbers. And there were 4 key quantum numbers that were defined: an angular quantum number L, magnetic quantum number ML, and magnetic spin quantum number MS. In the same decade as the work of de Broglie and the experiments that proved his work, Erwin Schrödinger in the late 20s was looking to improve on what de Broglie had already started. His work was very much centered around developing a mathematical relationship between the matter wave and the properties of electrons. Further to this mathematical relationship that Schrödinger was looking to develop had to also account for the behavior and nature of all electrons in all elements. Effectively, what he was looking to do was account for these other quantum numbers as well, particularly the middle two. What Schrödinger understood was that electrons in an atom would have different properties and a different combination of quantum numbers. His equation, which I'm sure we can all agree is much more complex than the de Broglie equation, accounted for the first 3 quantum numbers, NL and ML. Not magnetic spin though. When you manipulated this equation in a very particular way, what you would yield is a set of information which could plot in 3 dimensions the probability of finding an electron in an atom. In other words, we could start to plot probability density. Instead of thinking about electrons as Bohr did in these discrete orbitals, instead, the Schrödinger equation suggests that we have electrons existing in discrete energy levels, but the location of the electron at any point in time could be anywhere that is marked with color in this diagram. However, there would be a probability density. There would be some areas of the atom in which you would be most likely to find an electron with these particular quantum numbers. As such, we could look at the behavior and characteristics of each of our electrons and map out the probability density for each of them. So for example, if we had electrons with principal quantum numbers 1, 2, and 3, there will be areas of high probability, say in the center for all of them, where the electron could exist. But for our energy level 2s and 3s, there are also outer rings where there's a high probability of finding this electron as well. Again, this comes from a manipulation of the Schrödinger equation to generate these probability distributions. The most simple types of probability distributions are spherical in shape, when you actually pull out all the math and construct a 3-dimensional shape based on the mathematics and the functions. And these are associated with what we call s orbitals. Now, this visual here would probably be quite familiar to some of our chemistry students and may have been something that you looked at last year. Electron orbitals are not just spherical in shape like these S ones. There are many other types of configurations and geometries too, and these are dictated by much more complicated mathematics than our first orbitals. We also have p orbitals, which are essentially 2 lobes, d orbitals, which are usually 4 lobes, and f orbitals, which contain several lobes. In each of these pictures, anywhere that is coloured is essentially highlighting an area of space where the electron is most likely to be found. As we looked at in the previous video, the de Broglie equation was only able to quantify the location of an electron based on essentially drawing a circle based on a given radius. However, as I've alluded to, and as we can see here, the Schrödinger equation is significantly more complex and is able to plot out geometries in 3 dimensions, with, in some cases, very complex shapes. As such, we are not unpacking the mathematics that lead to these geometries. All we need to have an understanding of is that the mathematics, these shapes, and is based on manipulating the Schrödinger equation in a way where these geometries that we can map out are indicative or show the potential locations of an electron in that particular orbital and the likelihood of it being in a particular spot by probability density. So let's have a look at the quantum numbers which actually feature in the Schrödinger equation. The principal quantum number describes the size and the energy of the orbital. As we talked about before, this is the same as the Bohr model. This doesn't dictate any of the shapes that you might have for an orbital, but instead, the same shape orbital can get larger and larger and larger as we increase our principal quantum number, our n value. We also have an angular quantum number, L, and this describes the shape of the orbital much more clearly. And this factor is what gives rise to s orbitals, p orbitals, d orbitals, and f orbitals. S, P, D, and F orbitals are given quantum numbers 0, 1, 2, and 3 respectively. We also have the magnetic quantum number ML, and this describes the orientation of the orbits in 3-dimensional space. These can be given as whole integers, and they are positive or negative. For the P, D, and F orbitals, which have, for the most part, the same or similar geometries, just rotated or orientated in different ways through space, it is these magnetic quantum numbers, these ML values, which change the relative positions of the orbitals. For example, this orbital here, P-1, features lobes which run through the x-axis. The P0 orbital has lobes running through the z-axis, and the P1 orbital has lobes running through the y-axis. It's worth noting here too that in this diagram, the -3 in subscript is the magnetic quantum number. So what can we conclude from this? Well, Schrödinger's equation explained the wave nature of electrons. His mathematical framework was able to account for many properties of the electrons based on their quantum number, and also meant that we could predict the nature and properties of an electron based on their quantum numbers, based on their orbital size and electron energy, as well as their orbital shape and their orbital orientation. By using the equation to get probability distributions of these orbitals, this paved the way to be able to explain electron configuration, essentially where all the electrons are and where they're placed. This is the focus of Module 1 in the Chemistry HSE course. But it's not the only place that we can use this orbital concept to understand the properties of chemistry. For example, when we look at chemical bonding of organic substances, which is reflected in Module 7 of the Chemistry course, p orbitals explain the bonds that form between carbons in a chain. If there's a single bond, there's a direct overlap of p orbitals, but for double and triple bonds which are less stable, these are formed by pairs of p orbitals which are not geometrically aligned or overlapped. It also gives us some information and insight around the shape that molecules take, as well as behaviors in chemical reactions. Even though, again, we have taken a really big jump in our understanding of electrons and their behavior, there are still limitations to this model. And while it's important to identify them, it's also really important to understand that this is kind of our limit in this course for understanding the behavior of electrons. So taking anything any further is definitely beyond the scope of the course. However, we should acknowledge that the Schrödinger equation does not account for relativistic speeds. And it is relativistic speeds that explain the hyperfine splitting that we can see in spectroscopy. Further to this, scientists had an understanding of magnetic spin at this time, but the Schrödinger equation did not account for it. There was some work that quite quickly followed on after Schrödinger, and that was the development of the Dirac equation. Through this equation, which again is even more complex than the Schrödinger equation, these ideas of relativistic motion and magnetic spin were both accounted for. However, this is well beyond the scope of the course. I do want to spend a little bit of time at the end of this video, though, looking at the Pauli exclusion principle, which was actually introduced before the Schrödinger equation. It was Pauli who introduced the idea of magnetic spin. It was this concept which led to his exclusion principle, and that was that no two electrons inside the same atom could have an identical set of quantum numbers. What that meant was that the properties of each electron in a single atom all had to be unique. Without quantum spin, there would be a little bit of an issue here. Quantum spin is an interesting one. It's quite an abstract property, particularly based on how we use the word spin, because it's not actually directly connected to this idea of an electron spinning around and spinning maybe in one direction, which is spin up, and spin down, which is the other direction. Instead, it is an intrinsic angular momentum. Again, not something that we need to dig particularly deeply into. To finish, I would like to explore how quantum numbers can be used to describe electrons that may sit in a series of p orbitals, and demonstrate how the Pauli exclusion principle can be applied to ensure that all electrons that we are going to account for here will all end up having a unique set of 4 quantum numbers. So the 3 orbitals that we're going to look at here are px, py, and pz orbitals, also referred to as p-1, p0, and p1. This little notation here accounts for the L and ML values, which is the angular quantum number and magnetic quantum number respectively. In this scenario, we're going to say that the principal quantum number is always going to be 1, that the orbitals that we actually have are not just any p-1, p0, and p1 orbitals, but rather 1 p-1, 1 p0, and 1 p1. This is because there are other high energy p orbitals that also exist, which are larger than the p orbitals with a principal quantum number of 1. Now, each orbital, as it says on the left, is going to have 2 electrons. And each of these electrons is going to have a principal quantum number n, an angular quantum number L, a magnetic quantum number ml, and a magnetic spin quantum number ms. Now, in this scenario, each of the p orbitals is going to have a principal quantum number of 1. All of these will be identical and will not be a differentiating point here. The angular number is also going to be the same. For p orbitals, we always denote a p orbital with an angular number of 1. We will start to get some differentiation here with the angular quantum number because each of the orbitals, while they have the same shape, occupy a different area of space. At this point, the Pauli exclusion principle has not been satisfied because while we have unique sets of electrons with unique combinations of quantum number because of their different angular numbers, we have identical pairs of electrons at this stage based on their first 3 properties. The Pauli exclusion principle states they cannot have an identical set of quantum numbers, and this is where magnetic spin comes in. For the 2 electrons which exist in the same orbital, one of them is going to be spin up and one of them is going to be what we call spin down. They're going to have quantum numbers of +0.5 and -0.5 respectively. And this will also apply to the other pairs of electrons that we have in our other p orbitals. So as we look at our 6 electrons at the end, as we go down our column, we will find that while there are similarities in the quantum numbers for these electrons, they all have a unique set of 4. Because they are all 1p electrons, they all have the same principal and angular quantum number, but their combination of magnetic and magnetic spin numbers are unique. And finally, just to show you an example of an orbital that's completely different to our 1p orbitals, I'm going to add one more particle to our table. Let's do a circular one, an s orbital, and we'll say that it is the 2s orbital. This orbital is also going to contain 2 electrons in it as well, E1 and E2. Our principal quantum number here is 2, which means that there would also be an s orbital which is smaller than the 2s orbital. Its angular number, given that it's an s orbital, is 0. Because there's only one s orbital, it also means that there is only a magnetic number of 0. which means, again, that these two electrons have the same first three quantum numbers. The only way to distinguish between them is by their magnetic spin. Thank you very much, everyone. In the next video, we are going to go along a slightly different path. We're going to be moving away from developing our understanding of electrons and focusing again more on the nucleus. We're going to be looking at the fundamentals of nuclear reaction as well as the concept of radioactivity and half-life. But until then, have a good one.